Hello and welcome to the solid state videos, and this is part 3 of 10. This is going to be a little bit of a longish video, so have patience to go through the entire video. Here we are going to discuss about the various arrangements in the shape cubic. In the last part we talked about 7 possible shapes in which unit cells can exist and 4 possible arrangements in which you can have each arrangement in a particular shape. But we also said you cannot have more than 4 arrangements, and not all of them except perhaps orthorhombic have all the 4 arrangements. In this particular video we're going to talk about shape cubic, and we are going to look at the various arrangements possible in a cubic unit cell. So let's start. Cubic shape and arrangement is primitive. That was one of the unit cells that one arrangement that we talked about, primitive. So let's start with that. The primitive cubic unit cell is also known as simple cubic unit cell. So you can either call it primitive cubic or you can call it simple cubic. Now let's have a look at what a primitive cubic unit cell is defined as. So you got a cube and you got atoms there. As you notice, they're all present at the corners, and they're all the same type of atoms. So a primitive cubic unit cell is basically a unit cell in which all the corners are occupied by the same atoms, and these atoms are not found anywhere else in the cube. Only then you call it primitive. If any one of the corner atom is changed with another atom, it ceases to be called primitive cubic. Or if this particular atom is found somewhere else in the cube, again it ceases to be called as primitive cubic. So let's go back and see the definition. A primitive cubic unit cell is defined as a unit cell in which the same type of atoms occupy all the corners of a cube without any atom of this type having its center present on the center of any face or the center of the cube or anywhere else in the cube for that matter. Now let's also look at how the unit cell looks like. Well, again, going back to this particular view is called the unit cell shape view that we saw before with the 8 atoms at the corners. Now obviously in reality you will notice these lines won't exist. These are imaginary lines. So this is the unit cell shape view. Now what I'm going to show you is I'm going to number each of these atoms. All the atoms are of similar type, all positions are equivalent, but I want to show you that all positions are equivalent. I'm going to number these atoms randomly. I'm going to call this as 1, 2, 3, 4, 5, 6, 7 and 8. So there are 8 positions in a simple cubic or a primitive cubic unit cell. Now let's take this particular unit cell. Now focus your attention on this atom, this corner atom. Now from these positions, just decide which position does this atom occupy in this particular unit cell. Obviously it is position number 1. Now look at the unit cell which will be next to it, because remember unit cells have to be linking up. So in the next unit cell, what is the position of this atom with regard to these numbers? Obviously it is position 4. What about this one? Obviously position 3. The next? No, it's not 2 because I'm going to put this as the next. It is 7. Well, this is the one you were hoping for. What about this one? What is the position of this atom in this one? This is obviously position number 2. What about this one? Position number 6. What about this one? Position number 5. And the last one, position number 8. So effectively you have seen that every sphere would occupy all positions, different positions in different unit cells. So all positions are equivalent. That's the first point that you need to understand. Now, you will also notice that this atom is common to 8 unit cells. Its entire volume is spread into 8 unit cells. No volume of it is outside these 8 unit cells. And since in each unit cell, the volume of this sphere would be equal as in others, its entire volume is distributed between 8. So in one unit cell, it only occupies 1/8 of its volume. So the sphere, which occupies different positions in different unit cells, is being shared by 8 unit cells. Therefore, the volume that the sphere occupies in one unit cell will be 1/8 of its total volume. Now, there are 8 such unit cells, and the volume of each sphere would be similar to that of the other. So each will have a volume of V by 8, and there are 8 of them. So the total volume that the spheres occupy is the volume of one sphere effectively, which is 1V. This means that effectively there is one sphere inside. And this is called rank of the unit cell. The number of effective spheres in a unit cell is known as rank of the unit cell. So the rank of primitive cubic or simple cubic unit cell is 1. Now let me show you a 3D view of this. And this is how a primitive cubic unit cell looks like. Look at this. This is 1/8 of a sphere. This is how 1/8 of a sphere looks like. And can you see they're all in contact? So even though you were seeing some space there between the two of them, that was only to show you the shape, but actually they're all in contact. So this is simple cubic. Now I'm going to show you the contact. How are these atoms are in contact? So atom contact view. So I got a sphere here touching a sphere, and there are spheres at the back which is touching. This sphere is touching this one, and this sphere is touching this one as well as this one, but the diagonal atoms cannot touch. And I repeat these 4 on top, and I get a primitive cubic unit cell. Now if you look at the top view would look like this. Can you see the diagonal ones are not in contact? Only the adjacent ones are in contact. And this is the length of the unit cell, center to center. So if the length of the unit cell is A, then by definition A will be equal to 2R, where R is the radius of each sphere. So that is how the top view looks like. Now let's understand what layer arrangement must have happened from which we picked up this as the smallest unit. What was the arrangement from where we picked up this as the unit cell, the smallest repeating unit? So I'm going to show you that. So I'm going to show you the layer arrangement view. Now I'm going to place atoms one after the other in contact. And then I'm going to place them below this. And this is one entire layer. All the centers of the spheres are in one plane. This is one layer. Let's call this layer as layer Z or layer Z. Now we are going to create one more layer. Now we place another layer Z or layer Z on top of this one. So this is another one, and I'm going to slide it over, and it is placed right on top. Though right now you will not see exactly superimposing. I'm showing a little bit of a side view so that you can see the first layer also, but actually the second layer is exactly eclipsing, superimposing the first layer. So this is how a primitive cubic unit cell would look like. And this is the layer view, and the unit cell we picked up was these 4 and the 4 beneath this. This was the smallest repeating unit in this. So the layer side view would look like this. These are the side view of the layers. This is one layer. This is the layer on top. So from here we picked up these 8 as the smallest repeating unit. So this is the layer side view. So let's go back. And what does it say now? It says that the contribution of each corner sphere is 1/8 of an unit cell. The rank of primitive unit cell is 1, and if the unit cell length is A and the radius is R, then A is 2R. Now let's look at an alternative unit cell. When I say alternative unit cell, what I mean to say is, if you remember, when we discussed part 1, we said as beauty, the unit cell lies in the eye of the beholder. So you can start the unit cell from anywhere you want. So I want to test whether the cubic unit cell, cubic primitive unit cell may look a little different depending upon where I start the lines from. So this is what I do. I'm going to draw 8 cubes which are joined to each other. Remember those 8 unit cells we had in which one atom was being shared? So this was the atom that was being shared by the 8 unit cells. Now remember, the length is A. Now what I'm going to do is I'm going to start drawing lines from the center of this bottom left corner cube to the right corner cube, center to center. Now obviously if this length is A, so would this length be A, because from this point to the center of the face will be A by 2, center of the face to the center of this cube will be A by 2. So this is going to be A. And similarly, I'm going to draw from the center of this to the back center, then the left center, and then back to the forward center. So I'm going to draw lines starting from the center of the 8 cubes. And this cube also has the same dimension of A. But there is only one atom inside this. And if you remember, the rank of the primitive cubic unit cell was 1. So you can either have 8 atoms at the corners and nowhere else, or you can have 1 atom at the center and nowhere else. Effectively, this is also a primitive cubic unit cell. In reality, it looks like this because A is 2R. So if you look at this unit cell, it will actually be this one. A is 2R. This sphere is touching the faces at a point. From here to here is 2R, and that is also the length of the unit cell A. And of course, this is only possible if there are no atoms in these spaces. So A is 2R in this. So let's go back and let's see the next point. And we've already seen it. The alternative unit cell looks different from the previous one. In this, one atom is present at the center of the cube without any atom of this type having its center present on the center of any face or any corner of the cube. Now let's look at a term called packing fraction. Now what is packing fraction? Now packing fraction is defined as the fraction of the volume of a unit cell that is occupied by the spheres or the atoms or the ions or the molecules. So the packing fraction is equal to the total volume occupied by the atoms inside a unit cell upon the volume of the unit cell. Now remember, the total volume occupied by the atoms in the unit cell would be the rank multiplied by the volume of an atom. So the rank multiplied by volume of an atom upon volume of the unit cell. Now for a primitive cubic, rank is 1, volume of an atom is 4 by 3 pi r cube, and volume of the unit cell is A cube. And we already know the relationship between A and R. A is 2R. So I substitute A with 2R and I get 1 into 4 by 3 pi r cube upon 2r cube. R cube gets cancelled and the value I get is 0.523. This means that of the total fraction of the unit cell's volume, 0.523 is the volume occupied by the spheres, which means 52.3% of the unit cell's volume is being occupied by the spheres. Now 1 minus 0.523, that gives us 0.477. That's called the void fraction. So this is the space. 47.7% is the space occupied by empty space. It's totally empty. So let's go back and this gives us the packing fraction is 0.523. Now let's look at one more term called coordination number. Now, coordination number in essence is the number of atoms that an atom is in contact with. Now remember, we are assuming only one type of atom. We are not assuming any atoms in any other space. So it's only atom made up of one, a cube made up of only one type of atom. Now let's look at a cube. Remember, atoms are only at the corners and the corner atoms touch. So look at this atom. Which atoms does it touch? It will touch this one, corner, this one at a distance of A, this one at a distance of A. Remember, there is another unit cell beside it. There is this atom at a distance A. There's a unit cell at the back. This atom is at a distance A, and there's a unit cell on top of this having this atom at a distance of A. So basically it is touching 6 atoms, or you can assume that it is touching 2 atoms in every axis. X, Y and Z axis, it is touching 2 atoms each, to totally 6. So the coordination number of a primitive cubic unit cell is 6. Now what we're going to do is we are going to go back and check out the master slide and see what it has to say. Well, we've already seen it. The coordination number is 6. And the next part that we're going to look at is a density. Now, density of any unit cell is mass of the unit cell upon the volume of a unit cell. Now, unit cells, remember, have single or double or few atoms only. So the mass of an atom would be the molecular mass or the atomic mass of an atom upon Avogadro's number. So if you multiply the rank with the mass of an atom, that would give you the mass of the unit cell, and that upon A cube would be the density. So density of a primitive cubic unit cell, rho, is rank of the unit cell into molecular mass. Read the molecular mass as atomic mass upon A cube into Avogadro's number. So that was the primitive cubic unit cell. And the unit cell that we move on to the next arrangement that we move on to is called the body-centered unit cell. So let's check out the master slide of body-centered cubic unit cell. Let's say what it has to say. Curtains are falling. Now the first thing we need to understand is how is a body-centered unit cell defined as. Now a body-centered unit cell is defined like this. You got a cube and this is a unit cell shape view. In the unit cell shape view, you only see the shape, you do not see which atoms are in contact. Corner atoms, same type, and there is also an atom at the center. Its center is lying at the center of the cube. This is called a body-centered cubic unit cell. So how do we define it? Let's go back to the master slide. And a BCC, or a body-centered cubic unit cell, is defined as a unit cell in which the same type of atoms occupy all the corners of a cube and also the center of the cube, without any atom of this type having its center present on the center of any face of the cube or anywhere else in the cube for that matter. Now please also understand, if the corners are made up of type A atoms and the center atom is type B, you would not call it body-centered unit cell. You might call it body-centered type, but you cannot call it body-centered cubic unit cell. In fact, it would be primitive with respect to both, because if you remember the definition of primitive is either having 8 at the corners and that atom not being anywhere else, or that atom being at the center and that being not anywhere else. So it would be primitive with respect to A and primitive with respect to B. Now let's see how do these atoms contribute, what is the sharing, what is the rank, and what is the contact points. Again, the unit cell shape view. This is the BCC unit cell. Atoms are all at the corners and there would be an atom at the center too. The volume that a corner atom occupies would obviously be 1 by 8, just like primitive. And the volume that the center occupies would be completely 1 because it's right at the center. It's not being shared by any unit cell. The volume that a center sphere occupies in the unit cell will be its complete volume. So the total effective number of atoms or the rank will be 2, 8 into 1 by 8 plus 1. Therefore, the rank of a BCC unit cell will be 1 by 8 into 8 plus 1 equal to 2. Now let's see the contact points. How are the atoms in contact view? Now you got 4 atoms not in contact in the form of a square. Remember, they're not in contact. If these 2 are not in contact, even these 2 are not in contact. And I place one atom at the groove of these 4. It is touching these 4 and there are 4 on top, just like the first layer. So it's made up of 2 types of layers basically. Now of course one might wonder, how the hell is this hanging in space by being in contact with only one atom? Remember, this is only a unit cell. I'm not showing you the layer arrangement right now, which I will show you very soon. So let's see the 3D. And this is a body-centered cubic unit cell with only one type of atom. Can you see the corner ones are not touching? And this is 1/8 of a cube, of a sphere, sorry. And right at the center, this atom is in contact with 4 on top, 4 at the bottom. And also notice something else. Do you notice that this atom is not touching the face? I wish I could take you zoomed in. Is there a zoom in button here? Go to, let's see, let me go to here. Yeah, it's zoomed in. Can you see it is not touching the phase anymore? So A is definitely not 2R. In fact, A is larger than 2R. A is larger than 2R. So that is the body-centered unit cell for you. Now the next thing we're going to do is the layer arrangement and see how the layers are arranged. All atoms lying on the body diagonal of the unit cell are in contact with each other. So the body diagonal are in contact, and the body diagonal of a cube is root 3a, and that will be equal to R plus 2R plus R, that is 4R. So this is root 3a equal to 4R. So now let's see the layers. Now the layer arrangement view. Now I make a layer similar to the primitive one, except that the atom will not be in contact. Remember, in primitive they were all in contact, but now they are not in contact. Now let's call this as layer X. Now I'm going to place a layer Y by placing the atom at the center of this groove. And that atom will be of similar type, but I'll show it with a different color just to show you the different layers properly. But that atom will be same as this atom. So I'm going to place one here, and I'm going to place the atoms right at the grooves. And you will notice that even this layer resembles the first layer. The way this has been constructed is just like the first layer. Only thing is the placement is a little staggered. The placement is in grooves rather than superimposing the first. So let's call this as layer Y. So now we place a new layer Y on top of X. Layer Y has the same arrangement as X, but is put in the groove of X layer atoms. Now what we're going to do is we're going to repeat X. And now the atoms that I'm going to show you will be atoms which will be transparent. But remember, they're all the same type of atoms. So now we place layer X again on top of Y, and it's going to look like this. These are transparent atoms that I'm putting so that you can see all the layers, but they are basically of the type X. So X has been placed on top. So from the top view, it will look like this. Now I'm just shifting it. Just look at this. The top layer I'm shifting slightly so that you can see the bottom layer also. Now this is how the view looks from the top. 4 atoms and 4 on top, which are superimposing the first layer. If you look at the side view we've already seen. Not in contact, not in contact, not in contact, groove, 4 on top, and this would be the side view. So let's go back to the master slide and let's see what the master slide has to say about this. the master slide says that the contribution of each corner is 1/8 for a unit cell. The contribution of body center is 1 for the unit cell. Rank is 2. Root 3a is 4r. Now let's look at alternative unit cells. And let's see if we can get an alternative unit cell here. Well, in the case of an alternative unit cell, we again construct the 8 unit cells to which that corner atom was common to. It's going to take a while, have patience while the unit cell is getting constructed. I could have made the unit cells come in one go, but I wanted you to see how the unit cells are getting constructed. So now remember, this is the corner atom. In a body-centered cubic unit cell, corners you have and body centers you have. Now what I'm going to do is I'm going to draw the body-centered atoms of all the 8 cubes. Body-centered, back left, forward right, backward right, backward left, forward left. And now I'm going to join these, and can you see this distance is also A? And suddenly you'll find another unit cell of the same length A, but the only difference is the corners, this corner now has become body centered and the body centered have become corners. Can you see that? So this is what the alternative unit cell is. So the alternative unit cell looks just like the previous one, with the difference that the positions have changed. The corner becomes body centered and the body centered becomes the corner. So the alternate unit cell looks identical to the previous one, with corner and body centered atoms interchanged. So now let's look at the packing fraction. We know the rank is 2. So this is the basic definition. We're going to go through all the motions. Rank multiplied by volume of the sphere upon volume of unit cell. Rank is 2. Volume of the atom is 4 by 3 pi r cube. Now the volume of the unit cell is a cube, but you know root 3a is 4r. So a is 4r by root 3. So 4r by root 3 the whole cube. R cube gets cancelled. And there you go. You have got 0.68. 0.68 is the packing fraction. This means that 68% of the atoms of the unit cell's volume has been occupied by the spheres. So this is a more effective and a better packing than a primitive cubic, which had approximately 52%. And 1 minus 0.68, 0.32 is the void fraction. So let's go back to the master. And this will tell us that the packing fraction of a body-centered cubic unit cell is 0.68 that we just saw. The next thing that we're going to look at is the coordination number. And we've already seen that the middle atom was touching 8 atoms at the corners. So it was not a big deal to understand that the coordination number is 8. So this is touching 8. And this is similar to this, and as you can notice, this will be present in 8 cubes and it will touch 8 body-centered atoms just like it touches this one. So each atom will touch 8 other atoms. So the packing fraction, the coordination number in a body-centered cubic unit cell is 8. So the coordination number is 8. And let's look at the density. The density is the same logic. Only thing is the rank is 2 this time. So it's 2 into the atomic mass of the atom upon the Avogadro's number upon the volume of the unit cell, which is 4r by root 3 the whole cube. So that was the body-centered unit cell. And the next one that we go to is called the face-centered unit cell. It's face-centered cubic, shape is cubic, it's face-centered, and let's go to the master. So the bird flew away. Now let's look at what a face-centered unit cell is defined as. The face center unit cell is defined like this. You have a cube, the unit cell shape view. You have a cube having atoms at each corner. And the atoms are also being placed at the center of every square face. Can you see? Each phase center has been occupied by these spheres, and these spheres are not present anywhere else. So the definition is FCC unit cell is defined as a unit cell in which the same type of atoms occupy all the corners of a cube and also the center of every face of the cube, without any atom of this type having its center present on the center of the cube or anywhere else for that matter. Of course, other types of atoms can always exist in the space. It will be still FCC with regard to these type of atoms. So now let's look at the rank, the contribution. Well, this was the unit cell. Let me do it quickly. The volume that each of the corner occupies is 1/8, as we know, and the volume that each of this face center occupies is only half in and half out. So each face center has a contribution of 1/2, and there are 6 face centers and 8 corners. So 1/8 into 8 and 1/2 into 6, that makes it 4. So the rank of the unit cell is 4. Now let's look at the atom contact view. How are they in contact? Again, you see these 4 atoms are not in contact with each other. And now I'm going to place the atoms on top, not in contact with each other. And now I'm going to face the phase atoms. This is the phase atom of the back face, top face, right face, bottom face, left face, and the front face. So as you can notice, the phase diagonal atoms touch each other. So root 2a, R, 2R and R. So root 2a is 4R. All atoms lying on the phase diagonal of the unit cell are in contact with each other. They are in contact, and that is root 2a is 4R. So let's go back to the slide master. And it says the same thing. The contribution of each corner sphere is 1/8 of a unit cell. The contribution of the face center is 1/2. Rank is 4. Root 2a is 4R. Now let's look for an alternative unit cell. Is there a unit cell alternative to this? Well, when it comes to looking for alternative, we again have to draw those 8. So let me draw them quickly. These are the 8 unit cells. Now what I'm going to do is I'm going to draw only the face centered atoms. Face centered of these top faces of the bottom 4, top faces of the top 4. Face centered, face centered, face centered, face centered, and they're all face centered atoms. And I'm going to now draw the 2 corners here. Now just imagine a line joining these. Now, what is this atom? This atom is the face-centered atom of this face. Can you notice this face? Face-centered atom of this face. Which is this one? This is the face-centered atom of this face. Which one is this? Face-centered atom of this face. They are all face-centered. And which one is this? Face-centered atom of this face. This one. And I join these face centers. The edge length is A again, and it just looks like the face centered unit cell that we saw. Now what is the difference? The difference is it still looks the same, face centered, but the difference is some face centered have become corners, some face centered are still remaining as face centers. Just look at this. These were face centered initially. This was the face centered of this face. Now it has become the face centered of this face. So some face centered have become corners, some face centered remain face centers, and some corners become face centers. So this is how this plays out. So going back to the slide master, the alternate unit cell looks identical. to the previous one, with corner atoms being face-centered and some face-centered also becoming corner atoms. Let's look at the packing fraction. The packing fraction, well, let's go through the motions of the definition. And as we've already seen, rank is 4, that we've already seen, 4 into 4 by 3 pi r cube upon a cube. Remember, root 2a is 4r, so a is 4r by root 2. And if we solve this, we get 0.74. So the packing fraction of FCC unit cell is 0.74, 74% is occupied, much better packing than even BCC. And only 26% is free space. Void fraction is 0.26. And it has been found, and which I will prove later on to you, that the face-centered cubic unit has the highest packing fraction of all the unit cell. Face-centered cubic unit cell has the highest packing fraction of all the unit cells. So all shapes and all arrangements, this is the maximum. Master. And now let's look at this. First of all, tells us about the packing fraction. Now let's look at coordination number. And this is going to be a little bit interesting. Coordination number. Now this is going to be a little difficult to understand, so you have to pay attention to this very carefully. I'm going to draw one cube here and the corner atom here. First of all, I'm going to show you how many atoms the corner touch. Of course, the same number of atoms the face center would also touch, but I'm going to show them differently, separately. Now, remember, this corner atom touches every atom at the face center. It doesn't touch another corner atom. Only face-centered atom it touches. So let this be x-axis, y-axis and z-axis. Now, which plane is this? Guess. Don't you think it is parallel to this YZ plane? And there will be 4 face-centered atoms here. Now, I'm drawing them with a different color, but they're all the same type. Can you see it will touch these 4 face centers? Now, I'm removing them to avoid confusion. I'll bring them back later on. Now, tell me which face is this one? The horizontal one. Isn't the horizontal one XY plane? And won't you have 4 face-centered atoms here too? So that makes it 8 so far. Let's remove this. Now, which phase is this? Isn't it the XZ plane? It touches, it has got 4 face-centered atoms here too. That makes it 12 now. Obviously, in an XYZ plane, XYZ axis, you'll have only 3 planes. Each plane it touches 4, so the max it touches is 12. Now let's bring back all the atoms. So this is the 12. So the coordination number is 12. Now that we have seen for the corner atom. Now let's try and figure out how much is the coordination number for a face-centered atom. And obviously that should also be 12, but we need to know how is it 12. So this is one unit cell. And this is the face-centered atom for which I need to show 12. Now what it does, it touches these 4 corners, which is not a problem. You know the corners and the face centers touch, so that makes it 4. Now look at a unit cell, which is above this. There are 4 face centers on the sides of this. This touches these 4 as well. Now why it touches these 4 as well is something I'm going to show in a short while. But please understand, it will touch these 4 as well. So it is touching these 4. 8. Similarly, it will touch these 4 face centers, the side face centers of the unit cell, bottom unit cell. That makes it 4 more, and that is 12. Now let us understand why it touches these face centers. Now definitely we know it touches these two definitely touch, the corner and the face center. Now remember, root 2a was 4r. Remember? Root 2a was 4r. So if root 2a was 4r, if root 2a was 4r, what would be 2r equal to? It would be root 2a by 2, which will be a by root 2. Now what is 2r? 2r is the distance between the centers of 2 spheres when they are in contact. So, since 2r is a by root 2, that means if two atoms have centers at a distance of a by root 2, and since a by root 2 is 2r, they will automatically be in contact. So if I can prove that the center of this sphere and the center of this sphere are at a distance of a by root 2, that would make it 2r, and therefore they would be in contact. And that is exactly what I'm going to do now. So this is the unit cell. Top face center, side face center. Now what is this distance equal to? Isn't it a by 2 to the center of the unit cell? What is this distance equal to? Isn't it also equal to a by 2? And therefore what is the hypotenuse equal to? A by root 2. And if two spheres have a centers at a by root 2, they will be in contact. So that is how the face center will touch the side face centers. So now let me show you the 3D. And now look at this face center, top face centered, touching the four corners. Can you notice the face center is also touching the side face centers? Where is that go to here? Can you see it is also touching this? The side face centers. It's in contact with those side face centers. So that is how a face center unit cell looks like. So the master slide tells us that the coordination number is 12, which we just figured out. And then comes the density part. And here the rank is 4. So it's the same formula with a different rank. And that finishes off the 3 varieties of arrangements in cubic. Now, why don't we have the end-centered? Remember there was a 4th arrangement, end-centered in cubic? That is what we have to figure out, and that we will figure out in the next video. Now there are totally 7 shapes, and in each shape there are 4 types: primitive, body-centered, face-centered and end-centered. So that gives us a possibility of 28 types of different unit cells. But in reality, only 14 of them exist. And these are called Bravais lattices, after the person who discovered this. Now, what happened to the other 14, the missing 14? Well, the missing 14 will actually exist in these 14 itself. They're not actually missing. So actually, the missing lattices are already there. Each of the 14 missing lattices are equal to those that already exist as Bravais lattices. And this is exactly what we're going to see in the next video. The rule that is followed to select is symmetry and size, meaning that end-centered cubic BCA doesn't exist. Now, why doesn't it exist? Because it already exists in the form of some other shape and some other arrangement. It's already there somewhere. Now, the question is, why do we call it that and not call it end-centered cubic? So all of that we'll see in the next video. So right now I'm going to show you what are the lattices that actually exist. So the lattices that exist are in this table. There are 7 crystal systems, and these are the Bravais lattices. Cubic contains 3. Orthorhombic, remember I told you, is the only one which has all the 4. Primitive, body-centered, face and end-centered. Rhombohedral has only 1. Tetrahedral has 2. Hexagonal has 1. Monoclinic has 2. And triclinic has only 1, because that was the worst possible symmetry you could ever have. So that is the end of this video. In the next video, what we're going to find out is what happened to the missing lattices, where are they, what are they equivalent to, and why did we select a certain name and not another for those particular unit cells. Please subscribe to this channel in case you haven't already. If you do that, you get immediate intimation of all the videos I post. It encourages me to make more and more videos since you like them, and if you do like them, please hit the like button too. So subscribe and like this channel and this particular video. I hope this video helped you in understanding in some way the different arrangements of cubic unit cell. So this is Kalyan Kumar signing off. All the best and have a wonderful day, and thank you for watching.